Okay, section 8.3 is on geometric sequences and series. Remember, a geometric sequence is when you are multiplying by the same thing to go from one term to another. Geometric sequences are very much the same as exponential functions, except that a sequence is discrete, like we talked about in arithmetic, right? It would just be dots on a plane, whereas a function would be continuous. You would connect the dots. A1 is your first term. R is your common ratio if you're talking about sequences, but it's also your multiplier if you're talking about exponentials. The way to get R is to take any term and divide it by the term before it, right? So if I was going 2, 4 times 2, 8 times 4, 16. I know it says take A2 and divide by A1. That's a way to do it. 4 divided by 2. I was multiplying by 2 every time. But I could also take A4 and divide it by A3. 16 divided by 8. You're multiplying by 2 every time. And you would have figured that out even if we hadn't told it to you. It's pretty logical. So, given the rule of the geometric sequence, you can tell it's a geometric because of the way it's written and the exponent. Determine the initial term. So, if we were plugging in 1, a sub 1, we would be doing 7 times 1/3 to the 1 minus 1, which is 7 times 1/3 to the 0. Anything to the 0 power is just 1, so the initial term is 7, which it says that right here. The initial term is going to be that thing in front of the parentheses. The common ratio is going to be the 1/3. If you're multiplying by 1/3 over and over again, that's your common ratio. List the first 5 terms. Okay, again, we gave you 4 of them. But figure out what's happening. How are they going from one term to the other? So if you don't just see it, remember you can take this one and divide it by that one. So 1/3 divided by 1/6. This is a mathematical disaster. We do not put fractions in fractions. We keep the first term, flip and multiply by the second term. That's 6 over 3. So they're just multiplying by 2 every time. Times 2 is going to give you 2 over 6, but that reduces to 1/3. Times 2 is 2 thirds. Times 2 is 4/3. Times 2 is 8/3. There's your 5th term. Determine the rule. So a sub n is, our first term is 1/6 times, we're multiplying by 2 every time, and then we're going to raise it to the n minus 1 power to guarantee that we get that 1/6 back out when we plug in 1. Determine the 11th term. Definitely need a calculator for this. A sub 11, 1/6 times 2 to the 11 minus 1. So when you type it into your calculator, you're doing 2 to the 10th. Make sure you use parentheses the way it's written. I believe you get 512 over 3. Okay. Given the following sequence, determine the geometric rule. So what is happening from 162 to 54? What are they doing? So again, if you can't see it, you can take any term and divide it by the previous term. 54 divided by 162, that's going to give you 1/3. So they are multiplying by 1/3 each time. So an is the first term times multiplying by 1/3 each time, raised to the n minus 1 to guarantee you get that 62 back out every time. Find the 12th term, plug in 12. Which means you're going to do 162 times 1/3 to the 11th. You have to put parentheses around your 1/3. I believe that gives you 2 over 2,187. Number 4. The second term of a geometric sequence is 6. Well, I already know I need to start writing stuff down. So, not the first term, but the second is 6. And then the 5th is 48. So second, third, 4th, 5th is 48. Determine the rule for the sequence. Okay, so what do I know? I know that if I take 6 and I multiply by something, r, and then multiply by something again, r, and then multiply by it again, r, I'm going to get 48. So 48 is going to equal 6 times r cubed. So if I divide by 6, 8 equals r cubed. The cube root of 8 is 2, so r is 2. So now I know r, now I need to go back and find what would have been the first term. So if they're multiplying by 2 each time, divide by 2, this must have been 3. So a sub n is 3. We found r to be 2, n minus 1 for your exponent. 8th term, plug in 8. 2 to the 7th times 3, 384. Okay, sum of a geometric sequence. So for geometric, we have a finite geometric sum and an infinite geometric sum. And I will talk about why in a second. Also, I do not have a cute little reason to show you why geometric sums work. Feel free to Google it, but there's not something that's at our level to explain why geometric sums work, so I'm just going to need you to run with it, memorize it. Here's the finite, and here's the infinite. Let's do a finite one first, and then I'll talk about the infinite in a second. So, from our formula, we need a1, r, and n. a1, r, and n. a1, notice this time sigma starts with a 1 down there. That's why I put a 1 here, right? They have to match. So a1, 3 times 2 to the 1 minus 1 is just going to give us 3. We could have just seen that. We didn't have to do the math. R is the number the number with the exponent on it, 2. And n from 1 to 5, 5 minus 1 plus 1, n is going to be 5. So our formula is, and you can also write it like this if you prefer. You can put the a1 in the parentheses. 3 times 1 minus, r needs to be in parentheses, 2 raised to the nth power, all of these parentheses need to be there, and then divided by parentheses, 1 minus r again. All of the parentheses that you see have to be there in order for your graphing calculator to give you the correct answer. The correct answer, that is 93. So that means if I had listed out all the numbers in this sequence, what would they have been? 3, 6, times 2, 12, blah, 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 and added them together, I would have gotten 93. I can always add up a finite number of terms, right? Finite means there's a beginning and an end. Whether it takes me a long time or not, I can do the math on adding up 20 terms, 50 terms, 100 terms. So let's do number 2. Find everything you need. It starts at 1 again, so a1, just going to be r, we need to know, and n, we need to know. So what is a1 going to be? So this is the number with the parentheses on it. So the imaginary a1 in front is just 1. R is the 3. And n from 7 to 1, 1 to 7 is going to be 7. So 1, I know it's not necessary, times parentheses 1 minus parentheses 3 to the parentheses 7 parentheses over parentheses 1 minus 3. See if you can get the correct number out of your calculator. You should get 1,093. These get big really quick, right? Because we're multiplying by something over and over again. So the sequence is getting bigger, and then we're adding them up. So the answers are going to be pretty big. So those were finite, from 1 to 7, from 1 to 5. Here's another finite one. Why don't you pause the video and do this one on your own? So when you unpause the video, my solution will be on the screen, so make sure you pause it. Okay, so hopefully you noticed this time they wanted us to start at 3. A1 is not what we want. The starting term is A3, which is not just this number, but it's literally what you get when you plug 3 in. So that you start with -8, and then R is the number in the parentheses, and N is 4. You should get -120 because we're adding up a bunch of negative numbers in this problem. Okay, let's talk about infinite. I really hope you guys are listening to this video and not just watching it, because there's about to be a real big pause on my writing. Let's say that I told you if you came in at 7:15 every morning, actually, let's just say 6:30 every morning, and the first time you came in, I gave you $1. And then every time after that, I double it. So I give you $1 the first time, then $2, then $4, then $8, then $16, then $32, then $64. Are you ever going to stop coming to see me in the morning? Obviously the money gets more and more, and those of you who are money focused would say no, right? I'm going to give you more money every single time you come in. It's always going to be worth your while, and in fact, it's going to be more worth your while as time goes on, because the number's getting bigger and bigger. For numbers that are getting bigger and bigger, like in my example, doubled, there is no way to find the sum, because it's getting bigger and bigger every time. You're always going to come in to get that money. I cannot find the sum. No sum exists. It's infinite. However, if I started you at $64, and then I said the next time I'll give you, what's half of that? $32, and then I'll give you $16, and then I'll give you $8, and then $4, and then $2, and then $1, and then 50 cents, and then 25 cents, and then I'll like round up to 14 cents, and then 7 cents, and then I'll round it up to 3 cents, etc. Are you ever going to stop getting up at 6:30 in the morning? Is it ever going to be not worth your while? For some of you, you probably would have stopped coming in at the $4 mark, right? At some point, the money is so small and so insignificant, it's not adding to your sum. When that happens, R is between, or maybe I shouldn't say between, the absolute value of R is less than 1. When the money gets so small, this is a fraction. This is a fancy way of saying a fraction. But like, we can't say a fraction because 3/2 is a fraction, and that is not less than 1, right? So be careful when you call it a fraction. But when R is a fraction less than 1, eventually the amount you're adding is so small, so minuscule, that it doesn't even matter. It's not even changing my total. When that happens, you can find the sum, and this is the formula for it. It's a way easier formula, but you have to check R. You have to check this. If R is bigger than 1, there's no sum. And that could be a test question. So where are we? We're here. I see the infinity sign. That's how I know it's an infinite sum. My formula is a 1 over 1 minus r, parentheses down there. Always use parentheses in the denominator. You see the infinity, so we only need a1, and we only need r. This time it is starting at 1, so a1 is the 35, and r is the 1/5. But I have to check that that is between -1 and 1, a fraction less than 1. It is, so I'm going to put a little check mark. So the sum, the infinite sum, no matter how many times you keep coming into my classroom, this is a different problem, but is going to be 35 over 1 minus r. Sorry, 1 minus 1/5. Use all the parentheses appropriately, and you should get 43.75 or 175 divided by 4, if you'd rather. As long as the decimal's not repeating, this is an acceptable answer. Fractions, if you can't write it as a decimal. Okay, so see if you can do number 5. I see an infinity sign. It is starting at 1, so a1, and that is just the 7/10. R is the number in the parentheses. That is definitely a fraction less than 1, so it does have an infinite sum. 7/10 divided by parentheses 1 minus 1/10. If you carefully type it in, you're going to get 7/9 or 0.7 continuous. I do want to show really quick how you can get that without a calculator. So we were at 7/10. If I do 1 minus, so like 10/10 minus 1/10, I get 9/10. You can flip and multiply, or when you have a fraction over a fraction with common denominators, they cross out, and that is how you can get 7/9. And then one thing you can do with infinite sums is this infinite sum gave me 7/9, but that is 0.77777777. So you can make repeating decimals. You can write them as infinite sums. Okay, so if we want to do number 6, write 0.21 repeating as a fraction, we should look at what we're actually talking about. 0.21 repeating. That's I guess 0 point if you want to include your zeros, right? 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, etc. So if we look at that spread out, that's 0.21 plus, I need to cover those with zeros, and then another 2, 1, plus, I need to cover those with zeros, and another 2, 1, plus 6 zeros, and another 2, 1, etc., right? That would go on forever. So if we look at each of those and start turning them into fractions, 0.21 is 21 divided by 100. The number of decimals you have is the number of zeros you have. So this one is 21 divided by 4 decimals, so 4 zeros. Plus this one is 21 divided by 6 decimals, so 6 zeros. We're at 1,000,000 now. Plus 21 divided by, this should be 8 zeros. Plus dot dot dot, it goes on forever. So then if we start breaking that down even further and we notice the pattern, that's 21 over 100 plus, this is 21 over 100 squared, because the exponent tells you how many extra zeros you're going to have. So if I have 2 zeros and I square that, I'm going to have 4 zeros. Plus, this one is 21 over 100 cubed, plus 21 over 100 to the 4th, plus dot dot dot, on forever. So then if we look at it, I forgot my bar, 0.21 continuous, that is just the sum of I from 1 to infinity, because this goes on forever, of 21 over 100 raised to that nth power, or that I power. So then that also means that this is I from 1 to infinity. If it makes you more comfortable to put the 21 out front, of 1 over 100 to the I power. And then since that's an infinite geometric sequence, and R is definitely a fraction less than 1, we should be able to find the sum of that. See if you can plug that into your sum formula. So we have A1, plug in 1, 21 times 1 over 100. The first is going to be 21 over 100. And up here, those 2 decimals right here, that's always going to be your A sub 1. R is the number in the parentheses, 1 over 100. And then again, back at the top, if there's 2 decimal places, you know it's going to be 1 over 100. If it was just like 0.4 repeating, one number repeating, that's going to be 1 over 10. If it was like 0.257 repeating, that would be 1 over 1,000, because there's 3 decimals repeating. So our sum is going to be 21 over 100 divided by 1 minus 100, 1 minus 1 over 100, which is 21 over 100 divided by 99 over 100. The hundredths cross out, and that's 21 over 99. So the decimal 0.21212121, or 0.21 repeating, is equal to the fraction 21 over 99. Technically, we could have reduced that also. Divide by 3, right? This is also 7 over 33. Okay, that's it for today. We will practice this more in class, and I hope you guys are doing good.